Okay, hello once more. Let's continue our lectural studies. Today we will discuss some further mathematical methods to deal with electrical circle. Let's conclude some previous material, first of all, to see the whole general picture. And then we'll move during this material. What situation do we have? We want to build some mathematical model to some equipment or electrical network. To build this mathematical model, we are making some assumption. We discussed them on the first lecture. Which type of source of energy do we have? Which type of consumer do we have? If it direct current or alternating current, do we take into account space dimensional or time variation or some parametrical variation of our object? Just first step to build mathematical model. Then inside these assumptions, the easiest type of model, we start from DC, direct current. And for such direct current, we discussed how then, after building mathematical equation, we could solve them, depending on the type of system. Generally, we have two types of system that called simple and complex. And just this simple means one source of energy, for example, one source, and complex, it's mean more than two sources, two or more sources of energy. Then, if it's simple, generally we have one approach for calculation to find the total resistance of the whole system, just calculate it. And if we know the total resistance, we could find current starting from this electromotive force from the source. And the main question, how to calculate the total resistance. For the complex circles, we have lots of methods. They generally grounds on the Kirchhoff law. We discussed previously Kirchhoff law, that total current in some point should equals 0, starting from the charge conservation law, and that total voltage in some closed loop, in some closed mesh, should also equals 0. It is restriction by the energy conservation law. And these Kirchhoff's law, they are enough to build the system of equation and to find the solution. But we could simplify such mathematics to make some improvements of our method, and such improvements could be in different ways. It could be such called mesh currents. Mesh currents method for calculation. It could be such called nodal voltage. Calculation. Also, it could be superposition method. And also, it could be such called equivalent generator. Generator method. Generally, mesh current and nodal voltage, it is just straightly transformation of Kirchhoff law, just by substituting substitution of unknown variables. But superposition and equivalent generator, it is little different methods. They are also grounded on Kirchhoff law, but they are generally used for different final goal. Mesh current and nodal voltage generally we use if we want to calculate everything, all currents, all voltages, all power, to calculate the whole system. Superposition is generally used as additional part of some other method if we want to differ the influence of different parts of the system. If we have a couple of sources and want to calculate the influence of each of source, we use superposition method. And also it could be implemented in other method at just one part. We will see it a little bit later. It could be just as independent method, or could be as a part of more general method. And equivalent generator, this method is most widely used if we are searching for one current in one part of system, in one branch. It could be quite useful if we are interested just in some part, not in the whole system, but just in some part. And here is the total our engineering apparatus, engineering, I think, methods that we could use to deal with system. When we have some task, we are choosing which method is the most useful, is the most simple, and which method do we need exactly, depending on the task. Also, what do we have additionally? We have transformation of resistances that we called, I think, or equivalent transformations. It is mean that some parts of resistances we could change, we could substitute by other type of connections to simplify our system. That's all that we have. For equivalent transformation, it is series connection, parallel connection, and what do we have also? Star delta connection at previous lecture. Three types of transformation of resistances. Then, if we have some task, first that we are looking on, how many sources do we have? If we have one source, we try to find the equivalent resistance. If we can do it, we are doing it, and then finding current. If we cannot do it, we are using additionally equivalent transformation to simplify our circle. And also, then we could find resistance and find current. In all tasks with one source, in any way, at last, at final step, we could find this resistance. The main question, or do we need to do equivalent transformation, or we could solve this task without it? It is the main question. But in any case, the solution will be grounded on the finding of total resistance. For if we have situation of couple of sources, then if some equivalent transformation could simplify our circle, we also doing them. If we can do it, we are doing, because it could decrease the number of equations, it could decrease our mathematics. If it is useful, we are using it. In any case, with it or without it, we are using one of these four methods. Or first to find the whole system, or last two if it is some specific task with specific unknown variables. we will see a little bit later for which type of tasks this third and fourth method will be useful. Generally, holding in our brain that we could use Kirchhoff law, but Kirchhoff law transforms in other four methods, and it is simpler to use one of these four, not the general form. It is the whole picture of our mathematical apparatus for circular calculation, everything that we have in our course, in our discipline. Then later, when we will move to the alternating current, this whole picture will be the same. That is why I concentrate such much attention on it. Everything from this picture will be the same for alternating current. The main question will be which type of alternating it is, if it's sinusoidal or non-sinusoidal. If it's sinusoidal, what can we do to return to these equations? Because all this picture, all this equation, it is for algebraic equation. That is mean that inside it we are using only plus, minus, divide and multiply. Divide and multiply operations. Only algebraic equation. Because in direct current, all variables was constants, and the type of mathematics just linear algebra. If we are moving to alternating current, our equation became differential. And because on alternating current, we have time dependence and derivative per time variable. And the main question will be how to return from differential equation once more to algebraic and to implement all our approach to algebraic case. If we will move a little bit further, we will see that we could do it using complex transformations, such called symbolic method. We could transform time variables in operator form in some operational functions, and the type of operator will be dependent from the frequency and complex number J. Because I in electrical engineering is pointed as current, in mathematics on complex numbers we use I, that is square root of -1. But in electrical engineering, because I is generally current, we are pointed complex numbers as J. And such operator variable will be J omega, whereas omega is frequency of oscillation. And we could transform differential equation into algebraic in operator form and use all this mathematics, everything from this. For non-sinusoidal current, we could do exactly the same, but with some additional step at the central part. If it is not sinusoidal, we cannot use complex transformation, but we could firstly transform this non-sinusoidal function in a Fourier road as a couple of sinusoidal functions as elements of the row. And after these Fourier transformations, we will have, using superposition methods, couple of sinusoids. And from all these sinusoids, we could implement complex numbers and transformation also to algebraic form in algebraic equation in operational form. It is just the general view what we will do during our discipline. But these additional steps, they will be a little further. In any case, we'll move to this picture. What for this point of time we discussed already. We discussed this part. Just one moment. Let it be here. We discussed this part, how to find the total resistance. We discussed completely this part, how to substitute one type of resistor to other type, how to transform the type of connection of resistors. And we discussed this part for here, finishing on the mesh current. It's everything that we have. For today, we will discuss nodal voltage. I think maybe with superposition method or without it. In any case, in the nearest lecture, our final goal to discuss the last three methods to complete this picture in general, to fulfill it completely. That is, what about our cars? Maybe if you have any questions, please welcome.
No.
Everything in general words is clear. What do we have and what we will use?
Yeah,
for?
clear.
Okay, perfect. Then let's return to some practical examples, some mathematical implementation of this. Then let's see nodal method. Because why it is called nodal? Because we have nodes as a connection of couple of branches. Here it is, we have some nodes as connectional point, and we could write the potential in volts, potentials of each of nodes, and write equations not in terms of currents, but terms of the difference of potential, that is mean voltage. And all our equations will be not in amperes, but in volts. This is our goal. As we see, firstly, Kirchhoff law. No, please. Some circle. If we are looking on some circle and looking on the implementation of Kirchhoff law, as we see, it is written for currents in amperes, for voltages in volts, if we are speaking about dimension. Then, if we are transform this type of equations, type of system into the mesh currents, everything is written into amperes as in volts. Sorry, here it is. In volts, where it is? A little bit later. Here it is, in volts. Mesh current on the resistivity equals electromotive force. All equations are written in volts. If we are moving to the second transformation of the same Kirchhoff laws into the potentials, right here, we are writing them in the opposite values into the amperes, as you see. volts per Siemens of conductivity equals amperes, equals current or electromotive force on the conductivity also in amperes. And the main question, how we are building this system, how we could implement the second method. Let's see. It arises from the current main formulation, because current equals applied voltage, divide on the resistivity, and the applied voltage equals voltage difference between the points plus or minus electromotive force if it is present in our system. If we will look on some example, on some circular model, and try to write any current as we want, for example, the first current. The first current just equals current source, the source of current, and it is just value in amperes that is already known from our conditions, initial conditions. Then, for example, if we are trying to find the second current. The second current, according to the main physics course, equals the difference of potential between point 2 and potential of point 1, phi2 minus phi1, divided on the resistivity of this branch, just the Ohm law. And current just equals potential difference or divide on resistivity or multiply on conductivity, as conductivity opposite value. The same we could write for any other branch in such circle. For example, for the third current, it equals potential difference minus source, because source in the opposite direction of current, and divide on resistivity. The same we are doing for the fourth branch, the branch number 4. Potential difference phi1 minus phi3 plus electromotive, because in this case electromotive is the same directed, and divide on the resistivity of the branch. If we have, for example, couple of resistivities, then we are adding these resistivities in the bottom part of the equation. And such operation we could do for all currents in the system, all current that we have. Then let's move to the next step. Let's save this data, this picture. Yeah, and then we wrote all currents from this system. Then we could implement the current Kirchhoff law to connect these currents into the equation. We could write for any nodal point. For example, taking point number 1. What do we see here? We see current I1 and I2 that inflow the node, and we see current 3 and current 4 that outflow the node. That is why we could write the Kirchhoff law for the nodal point number 1. The same we could do for nodal point number 2. For second point, we have 1 inflow current, I3, and 3 outflow currents, I2, I5, I6, that we could write I3 minus I2 minus I5 minus I6 equals 0. Just writing Kirchhoff's law for 2 nodal points. For the last one, we it is not necessary to write the equation because all variables are inside the first two already written equations, and the last node, which is pointed as ground, we don't need to write the solution. The number of equation always will be one less than number of nodes. If we have 3 nodes, that it will be 2 equations. If we have 5 nodes, it will be 4 equations. If we have 10 nodes, we will have 9 equations. Just the rule is just like that. Then, after we write these current equations, we will substitute the value of currents. Let it see. Pum, pum, pum. We are substituting all values of currents inside this system. Instead of I2, the value with conductivity, instead of I3, the value with conductivities from the third equation, and so on and so on. Just substituting all these conductivities values into our system. And we will have equations like these, and after it, firstly multiply all potentials on all conductivities, outclose the bracket, and then we'll group parts of equation just by the same potential. Because in previous step, they were grouped by conductivities, conductivity outside the brackets. But then we will transform the same equation by the potential. Inside brackets will be conductivities, but outside the potential. And after it, we see the form of, we could multiply on -1 just to transform minus into pluses, it doesn't matter. In any case, we obtain the form of equation in nodal potentials. It is the form that we want to obtain, the form for solution of the system. Let's compare it. Let's compare it with the mesh currents. For example, for some example with mesh currents, the form of system for solution looks like here. In the nodal voltage, the equations looks like here. Currents on resistivities or potentials on conductivities. Two different parts of method. Mesh currents and nodal voltages. In which case the method will be better for implementation. It depends how many nodes and how many branches or meshes do you have. Because every example you could solve or using mesh currents or using nodal voltages. Depending how many equations inside system you will obtain. For example, let's look on the example 5.3. We have 4 meshes. but inside one mesh we have current source, then in previous lecture we discussed that if we have current source, it decreases the number of equations by 1 because unknown current I44 just equals already known current J as initial data. And it means that in this case, we have only 3 unknown variables, 1, 1, 2, 2, 3, 3. That is why if we will use mesh, approach here, we will have system of 3 equations. If we want to use nodes, nodes method. For nodes method, we have 1, 2, 3, 4, 5, 6 nodes. One node will be we neglected in the system of equation. That is mean that we have 6 minus 1, 5 equations. For mesh approach, we have 3 equations. For nodal approach, we have 5 equations. That is why that for example number 1, the mesh approach is much better. Let's see the second case. In second case, we have 1, 2, 3 meshes. Also, we have current source, and we neglect the mesh with current source. We aren't making equation for this last mesh with J, but also we have using the mesh approach 3 equations. But for nodal approach, how many do we have? Only 1, 2, 3. 3 minus 1, it will be 2. For nodal approach, we have only 2 equations. That is mean for this case, the better is nodal method. For here, it is quite simple examples. And you may ask, okay, matrix 3 on 3 or 5 on 5, computer will do both of these matrices quite quickly. It generally doesn't matter which we will use. Also 3 or 2, matrix 3 on 3 or 2 on 2, computer will do both of these examples just almost in the same way. But if you have large system, this large system could include thousands or hundreds of thousands of elements. And for example, if you have 1,000 or for example million of elements, it is quite important which is better. Or for example, you may be, for some situation, it could be 1 million of meshes, but if lots of parallel elements, only 1,000 of nodes. And it is obvious that nodal method will be much more useful. Or you could see lots of serial connected elements with current sources. And for this situation, you could have, for example, 1 million of nodes, but not so many meshes. And the difference, if we are speaking about large systems, the difference could be quite obvious between these two methods. And also on computer time and quick response from this computer, it could influence just seriously. Because if we are calculating some general working system, okay, no problem, we have time, we could wait. But if we are speaking about such some monitoring of operation of system, if we are speaking about state conditions of system, then if we are monitoring some working modes, the most important thing is how quickly we could obtain the response from our measurement parts. And as for quick response, the complexity of calculation should be as simple as we can. That is why the difference could be important in this method. Then let's move for implementation, because here it is improvement of method, but you don't need to make all these steps. As you see, we are started here and moving further, finished here. But we don't need to write everything previously. It is just an improvement of the implementation of the method. It is from which basic ideas it is found. We could write the form of equation just in one step, just in this form, starting from the initial circle. Okay, here it is. How we could obtain this system at the first step, just from the circle. We are taking some basic point as 0 potential, let it be 0 volt. And we'll write the equation near point number 1 and point number 2. What we are doing? We are starting from the point number 1, and we taking the potential of this point, phi1, always with plus. It will be always positive. Then we are connecting all branches that near this potential and implement them into the equation. We should write conductivities of these branches, and these conductivities will be the opposite values of the resistivities. And resistivity of current source. The resistivity of current source is very big. For voltage source, resistivity is closely to 0. For current source, resistivity is infinitely high. That is why conductivity moving to 0, because we are dividing on infinity, and we could neglect it in our equation. Then what we are doing next? We are taking potential of all other points, always with minus. It will be always negative. We are writing phi2 and branches that connected between first and second potential. It will be 1 over R2 and 1 over R3. Then, if there are other potentials in this system, we are also taking them. In our system, we have only last potential 3, and in general, we should write minus phi3 on the branch that are connected the third potential with our main phi1. But because phi3 equals 0, according to initial condition, then we could also neglect it and don't write everything connected with this potential. If we look on the starting equation, the main potential with plus, 4 branches near this potential, one of the branch equals 0. We obtain this point. Then second potential connected with the first and branches between them. In first equation, everything will be connected with first potential. Here it is. The third could be neglected because it is equals 0. And at the last, we should write sources. We should write sources in our equation. All sources that are near the potential. We have source J, we have source J, it pointed to the source in the direction to the source. That is why it is with plus. Then we have source number 3. If we will look on the direction will be also to the potential. That is why it will be also with plus. Value of source divide on the conductivity of this branch. And the last one, the last source, E4, in the opposite direction, it should be with minus. E4 divided on the resistivity of this branch. That is how we could build the first equation. For the second equation, we are doing exactly the same. We are starting from the second potential at the main potential. Yeah. Please.
I have one question. In the second phi2, why just 1 divided by R2 plus 1 divided by R3? R5 and R6 not include?
Yeah, good question. Because the first equation, we are building only for the first potential. And we are taking only resistivities that are connected to the first potential. But R5 and R6, they are not connected with the first potential. That is why they are not included.
Okay, and but why phi1, the first phi1 include R2, R3, R4? I don't understand.
Yeah. Because, okay, just one moment, I will write from this. When we are writing equation to the first potential, we are taking only branches near the potential. Only these 4 branches will be inside the equation. And if you look, if you see, we have only branch with R2, branch with R3, branch with R4, and branch with J. Any other branches are inside this equation because the first equation are written only for the first potential. 5 and 6 will not be inside it. Why we are writing R2, R3, R4? Because on the main potential for which we are writing the equation, we are taking all branches, but then for other potentials, we are taking only branch that is similar and connected with the potential number 1. That is why for the first potential, we are taking all branches. For the second, we are taking only branches that are connecting to this first one. And for the sources, we also taking the branch with sources only connected to the first one.
Okay, thanks, I understand.
Okay, perfect. Thank you for question. Then we are writing equation for second potential, and the situation will be exactly the same, but for the second potential. For the second, we have 4 branches. And we are writing, first of all, always with plus, because the main potential will be with plus. For the second equation, the second potential is the main. And we are taking all branches inside it. It is plus R2 plus 1 over R3, 1 over R5, and 1 over R6. And as you see, in the second equation will be branches with R2, R3, R5, R6. One moment. Okay, will be will be branches with R2, R3, R5, R6, but will not be branch R4. In the that differs from the previous case. In previous case was R2, R3, R4. In this case, the branch near potential 2. Then we are taking potential 1. It isn't main for the second equation, because for the second equation, the main potential is potential 2. And it is positive. All other will be negative. That is why potential 1 is negative. And we are taking branches between 1 and 2. The branches 1 over R2 and 1 over R3. What do we have additionally? Also, we have potential number 3 that is connected with potential number 2, but potential number 3 equals 0. And instead of minus phi3, what should we write? We should write 1 over R5 branches near between 3 and 2, and 1 over R6. But because 3 equals 0, then we could neglect this part from the calculation. And it equals sources. The sources near branch number 2. It is source number 3 and source number 6. Sources near potential number 2. As we see, source E2 in the opposite direction, it should be E3. It is minus E3 over R3 and E6 plus E6 over R6. Which type of system do we have? Because in some more complex case, we could have equation number 3, equation number 4, and so on, depending how many nodes do we have. If, for example, in some system we have node number 3, node number 4, and some connections with these nodes, the 0 node will be node number 5, and we could obtain some further system. What do we have as the result? We will always have diagonal elements positive. It will be phi3, and here it will be phi4. And if we will look on this matrix form of equation, the diagonal part always will be positive. Here it is. Then also all other parts will be negative. All parts here will be negative, and all parts here also will be negative. Positive, negative, negative. How we could also check the writing of system? Between any potential, we have branches that are the same for 2 points. For example, branch R2 and R3 is the same branch for both of these points. That is why in the system of equation, we will have twice the same conductivity written twice. For the potential 2 near 1 and for the potential 1 near 2. It will be the same equation, but with different potentials. And it is mirrorly written near the diagonal. It is how we will see the result of the system. And also, we could see the same sources in the opposite, with the opposite sign. For example, if the source E3 is the same for first and second node, in the first case, it will be positive because the direction to the first point. In second case, it will be negative because the direction is opposite, comparably with point number 2. If we will look on the general form, what should we see? We will obtain something like that. The diagonal part of the potential, this here, always should be positive. Here is a mistake, it should be positive. It is just a editing mistake of this methodological book. The diagonal part always positive, all other parts always negative. These conductivities with the same index, they are called own conductivity. It means the conductivity of the all branches near node. If we write node number 1, the own conductivity, it means all conductivities from this node. For node number 2, in the second equation, own conductivity, it means all branches near this node. For example, if the third isn't 0, for the third conductivity, it means all branches near this node. Then with double index, it is called mutual conductivities, self-conductance and mutual conductance or conductivities. Mutual conductance, it is branches that are between 2 points, between point of first index and second index, between point 1, 2. For example, if it is mutual conductance, for example, 2, 3, that is mean between point 2 and between point 3, conductivity is between these 2 points. That is how general equation is built. For now, if you have any questions, please welcome. And if no, propose to make a 5-minute break, just a little bit to clarify our thoughts.
Okay, it's clear. No question.
Okay, perfect. Then small 5 minutes break, and after it, let's practice it on some example. Okay, just small. Okay. Is everything okay? We'll continue.
Yeah, okay.
Okay, perfect. Then let's see on practical example how we are doing it. The example number first, it is here. Then also we have example number 2. It's here. Then if we are looking on the example number 1, it is the same complexity, or dealing with mesh current or dealing with nodal voltages. Because example number 1, we have 3 meshes. One mesh with current source. For it, the equation isn't written. That is why we have only 2 equations for meshes. But for nodal voltages, we have first point, second point, and points between 3 and 4 could be connected in one general, because between them are 0 conductor and the potential will be equal. That is why we have 3 potentials minus 1, also 2 equations. And for this application, it doesn't matter which method we will solve it. Let's see how it will be for the nodal voltages. Let's save the picture to see it. And okay, what the algorithm is. First of all, we are writing potentials pointing phi1 and phi2. We will search for them. And phi3 equals 0. It is just initial data according additionally to all other initial data. We are searching for phi1 and phi2. Then after it, we are writing equations for both of these potential. For phi1, as we discussed, the self-conductance connected with 3 branches. Here they are 1, 2, 3. Also minus phi2, and mutual conductance with phi2 for the potential number 1, and source that is connected to this phi1. Then we are repeating the same for the potential number 2. The self-conductance of 3 branches. 1 branch equals 0, conductance equals 0. That is why 2 branches. And minus mutual conductance with branch number 1. It is here. Source that is connected to potential phi2. Here with this source. And as the result, we have 2 equations. The system, substituting numbers inside this system, and obtaining the value of potential for this system. For the view of the equations, how we write it. Is everything okay? Is everything clear?
Yeah, clear.
Okay, perfect. Then after we find the potential, we could find currents just easily using the Ohm law, because the situation is like that. We have phi1 20 volts, Phi2 40 volts, Phi3 0 volts. Any current will be voltage difference. For example, I2. I2 is 40 minus 20, divide on 10. It will be 2 amperes. For example, Phi5. Phi5 will be 40 minus 0, divided on 20. It will be also 2 amperes. Then, as you see, 4 amperes, divide in equal parts as 2 and 2. Everything okay, 4 amperes, the total currents. Then E4, 20 minus 0, divide on 10, also 2 amperes. And the last one, I1. For I1, it will be 20 minus 0 and minus electromotive force, because electromotive force in the opposite direction, minus 20 over 5 ohm. We obtain 0 over 5, 0 amperes. The last branch will be without current, will be 0. And all currents are 0, 2, 2, 2, 4. And if you want to check the Ohm law, everything, the Kirchhoff law, everything is okay. 2 amperes equals 2 ampere plus 0. 4 amperes equals 2 amperes plus 2 amperes. And here, 0 plus 2 plus 2 equal 4. In each node, the current Kirchhoff law is true. That is the solution for this task. Writing for current that I did here, and the same for powers. For power balance equation, we have two sources that generates power. We are taking electromotive on the current, but the current direction was opposite. That is why it is taken with minus. And current source on the potential difference, between points 2 and 3. This potential difference is positive 20 volts. That is, for current source, it is 4 amperes on 20 volts. For electromotive, current was 0 and electromotive 20. That is, power from the first source is 0 because of current. For the second part, it is 4 ampere on 20, or what it was, let's see, 40 volts. That it is 40 volts on 4 amperes, 160 watts. It is power balance of sources. Here it is. Okay, here it is written. Perfect. Then for the consumers, the same square of current on the resistance. First current, 0 in square on 5, 2 amperes in square on 10, 2 amperes in square on 10, twice, and 2 amperes in square on 20. In total, 160 watts. Power balance is true. Everything that we generate, we consumed by resistances. It is how it is solved on the nodal voltages. Let's do the same for example, mesh currents. To compare, just that number will be the same. What we have? We have first mesh, for example, second mesh, and the last mesh as 4 amperes. For the first mesh, we pointed it as double index. I11. On the both resistances, it is 15, 5 plus 10, 15 ohms. Then minus, because of the opposite direction, I22, and resistance 10 between them, and without any other current, because for the first branch we don't have connection with the branch number 3, and it is equal 20 volts. 20 volts. The second equation, I22 on the 10 plus 10 plus 20, it equals 40. Then minus I11 on the same 10 ohms resistivity on this branch. Then plus J equals 4 amperes on the 20 ohms, and equals any source equals 0. And here is our system. We have 80 with minus. What could we do? We could, for example, multiply on 4 the first equation. Then it is 40, 80, and 60. Then add both of these equations. 40 plus 40, 80 plus 80 with minus equals 0. 40 and 40 with different signs also equals 0. And we obtain that 50 I11 equals 0. It is mean that current I11 equals 0 amperes. Okay, if it equals 0, then let's substitute it in each of equation. We obtain that I1 disappears, and as we see, I22 equals minus 2 amperes. Then let's return to our system. Then we have current 0 here. I4 and I2 equals minus I22. It equals 2 amperes. I5 equals J plus I22. 4 plus minus 2 also equals 2 amperes. And we obtain the same solution using mesh current method. The same currents as we see in nodal voltage method. Which method is simpler for this case? It choice by you. You could choose any of this method because in any case you obtain the same number of equations. But for tasks, then the number of equations differs. You are choosing the method which gives you the less number of equations inside system. That is how it works. Any questions about this example?
No.
What's about you? No.
It's clear.
Okay. Okay, perfect. Then let's just for revision of material for make it even more clear, let's look the last example for this method. Example number 2, we are looking here. If we compare which method will be better in mesh current, we have system of 3 equations, 1, 2, 3. For the nodal voltage, we will have 1, 2, 3, 4, 5. We have 4 equations, 4 of them. For this case, mesh current, I think even, okay, no. There is some specific case because of electromotive force. I will tell it just now, but okay, yeah. Almost forgot. There is one restriction about nodal voltage. For the mesh current, the restriction is about current source. We neglect the equation near the mesh with current. But for nodal voltage, the restriction is about voltage source, is about ideal voltage source without resistance. If you look on the branch at the left, we have resistance here. Also, in previous task, near each source, you have resistance. Resistance here. You have resistance. But in case when you don't have resistance near source, what conductivity you will get? The conductivity should equals 1 over resistivity, but for this case, resistivity is only electromotive force. But resistivity of electromotive force is almost 0 because it has very small internal resistance. Then you are dividing on 0 and obtain infinitely high value of conductivity for this branch. And if you will substitute infinitely high value inside the equation, you cannot solve it. For example, imagine that for this case, you don't have resistivity. Then in branch with source E1, you have infinitely high conductivity. And ideal conductor, then it means in each of equation, you have infinitely high value and you cannot solve it because the value is infinitely high. How to deal with this case? For this case, you should write the equation in such form that this infinity will not take in the account inside the equation. How it should be? It should be by choosing the ground 0 potential. If you have resistivity, you choose ground potential in any point. You choose ground here and make equations near all other points. You could choose it here and write the equation to all other points. The grounding, it is just a coordinate system. It is just a 0 point on the graph, on the potential graph. But if you have case without resistance, you cannot choose the coordinate system, the 0 point in any point that you want. You should, in this case, always take ground near the source, always here, near minus potential of the source. After that, the point, if it is 0 volts, then point number 4 became the point of source, value is 7. And after it, you are making equation for rest 3 potentials, for rest 3 points. It is the restriction of the method. Let's see this restriction for more simple case. Let's assume, for example, that we don't have resistivity here. It will be the same situation, but okay. If we don't have resistivity here, what should we do? We should take a 0 point near the negative point of the source. It will be at the same point here, ground on the negative point of the source. And after it, this source increase 0 point on the 20 volts. That it means that I1 equals 20. Already known, because this source increase potential on the value of source. And that is how you don't take into the account infinitely high value of conductivity, because you don't make equation for the potential phi1, because you already know the value of potential. And you don't need conductivity inside equations. What will be at the last? At the last, you will have only one equation for only one unknown variable. You have unknown potential phi2. You are writing the self-inductance by 3 branches. You are writing mutual inductance to point number 2. Oh, sorry, to point number 1. And that's all. The only one equation in this system will be phi2 1/10 plus 1/20 minus phi1 equals 20. Then it's mean minus 20 on the 1/10 and equal sources. Sources 4 amperes, and that's all. From this one equation, you are identify the last unknown variables. It is about this restriction. The last example for today, just to see how it is implemented for this equation, you are choosing 0 potential here. Let's make the picture. Just 2 minutes and we will finish for today. You are writing 0 potential here. The value E7 already known here. Then writing equation for point number 1. Self-conductance here. Mutual conductance with minus with point number 2. Mutual conductance with minus with point number 3. Mutual conductance with E7. All mutual conductance with minus, there is no source equals 0. And repeating all this for other points. For example, for point number 2, self-conductance with plus, mutual conductance is with point number 1, with point number 3, and with point number 7, if it is present, but it isn't, with point 0. Mutual conductance with 0, you could neglect this point. And the last one, the last equation, number 3, self-conductance of this point in all directions, self-conductance, positive, 0 conductance from the source, negative conductance with point number 1, negative conductance with point number 2, and with point number with source, with 0 voltage because of grounding. And that's all. That all 3 equations for point number E7 for this point. For this point, you don't need to make equation because you already know it. You already know the value. It equals E7. That is why you don't write equation for point number 4. That's all. That's all. You could see this example in the form of equation here at the end of this lecture. Also, if you have only 2 points, we have only one equation. We don't have system, we have only one equation. And such simplification is called method of 2 nodes. You also could see it here, but the general idea, instead of couple points and system, you have only 2 points and one equation. And that's all. For today, that's all. The next time will be the superposition method. Star triangle we already discussed. The next time will be superposition method, superposition theorem. For today, that's all. Thank you for your attention.
Okay, thanks. Have a nice day. Bye.
Thank you. The same to you. Goodbye. Have a nice day too.